Okay, guys. So today we're going to continue on where we left off yesterday. I do apologize for not being in class today, but I am pretty sure that you guys are doing fantastic without me. Anyways, priority number one today is just kind of get an idea of experimental probability. I'll show you guys a couple examples of the difference between experimental probability and theoretical probability. And then the new objective, the one that we're going to focus on for today, is just the probability of compound events and how to do that mathematically. Make sure that you guys hand Mrs. Anderson your worksheet from last night. Now, if you didn't finish it and you need an extra day, talk to her about it, and then she'll write your name down, and she'll sign off that you can have an extra day. Let's begin. So, experimental probability. What is it? Well, experimental probability is going to be just the idea of the probability of any event is really a ratio, a comparison between the number of times something happened versus or over the total numbers of tries. This is similar to theoretical, but in experimental probability, we actually try it. We actually do the number of trials. So, for example, I know the NBA finals are going on right now. So, for example, if you have a free throw shooter, okay, let's say over the season he is a 65% free throw shooter. Now, that 65% free throw shooting could include the number of attempts and the number of made. So that's the ratio comparison between the number of how many tries and then how many times he out of that total tries he made, 65% of that. So that's not pretty good, because that's we know that. Remember that it's 0 means 0 chance, and then we go all the way up to 1 being 100% or more likely. So then we have that 50 or that 0.5, that 50%. So 65% is going to be, somewhere around here on the more likely side. Now, if I were to predict if he was going to make the next one or not, 65%, it's above the 0.5 mark. It's going to fall on the more likely. Now that is going to be more useful than theoretical, just because we actually counted how many times he tried and then how many he made. So. Experimental probability, here's another example, is found by repeating an experiment and observing the outcomes. So for example, the probability of heads is, before I jump into the experimental, we know that the probability of heads, and theoretically, is going to be 1 out of 2, right? Because it's 1 head favorable over 2 possibility. Well, on the screen here, though, we have probability of head 3 out of 10, okay? That means that we flipped it. We flipped the coin 10 times, and out of the 10 times, we have 3 heads, which means we also know that the other 7 times, we got tails. So tail shows up 7 out of 10 times, head goes out of 10 times, or 3 times, so which means if I were going to predict the next trial, 70% versus 30%, I'm going to lean more towards the tails, just because it happened more than the heads. Now, we figured that out by actually conducting an experiment. So that's the only difference between theoretical and experimental. So how can you tell the difference? Well, experimental, you toss a coin 10 times and recorded the results. Theoretical, you don't actually try it. Theoretical is always going to be the number of favorable over all possible outcomes. While experimental, you actually try 10 times and you record what you have, and then you can predict your future or your next event from there. Okay? So let's move on. Compound event. Now, I actually want you guys to write this down. Compound event is going to be 2 or more events. So someone please pause this video and have the students copy this down in their composition book. And then when they're ready, I'll move on. So compound event. It's basically 2 more events. Compound meaning more than 1. Okay. So there are 2 types of compound event. We have independent events, and then we have dependent events. Independent events are events that do not influence each other. So the probability of A and B, you would multiply. Okay. Dependent events that do influence each other. That's going to be A and then B. You also multiply, but then you multiply B after A. Now I'll go into a couple more examples from that. But independent events, flipping a coin, definitely independent event because one coin toss does not influence the next because it resets every single time. So that's the trick to independent events. Independent events means that my outcomes are always, it's reset before every try. And then dependent events, that is more than likely something like you'll see or you'll read something like without replacement. That just means that if I had a deck of cards, 52 cards, the probability of pulling an ace out of there is 4 out of 52. Let's say I pull that card out, it's not an ace, and I put it back in. Well, I reset. I have 52 cards in the deck again. That would be independent events. Dependent events is when you pull out a card, not an ace, you set it to the side, so now you have 4 out of 51. Instead of 52, you go down to 51 because you never replaced it. You just left it out, so you didn't. So that is without replacement. Things like coin tosses, dice rolls. Okay, those are all independent events because one doesn't influence another one. Cards and usually are dependent events because you can keep it out. Spinners, if you're spinning a wheel or something, that's always going to be an independent event just because it resets. Now, unless you take something out and then spin it. Okay, so let's get into the math part. Independent or dependent? You toss a coin twice. What is the probability of getting heads 2 times in a row? Okay, so now this is all theoretical. We're not actually doing it. This is experimental. So the first thing we need to figure out is if this is independent or dependent. This is flipping a coin, so every time you flip it, the coin is reset. So therefore, this situation is an independent situation. So we're going to set up trial 1 and trial 2. And this is a theoretical. I'm actually not trying it, but the first try, or theoretically speaking, to get heads, it's 1 out of 2. And the second time, again, to get heads, it's either going to be 1 out of 2 because it resets. I'm not going to be able to change the shape of the coin or whatever. So, well, compound event, mathematically, what is the probability of heads and then another head? So that would be something like this. Probability of heads, head is equal to 1/2 times 1/2 is equal to 1/4. Theoretically speaking, you have a 1 in 4 chance, 25%, or 0.25 2500ths of a chance of getting 2 heads in a row. Now, if you're going from 0 to 1, and 1 being 100%, and 0 being 0%, well, here's 50%. It's going to fall in the more not likely range. To be exact, it will be in the quarter. Okay? So the math that we're doing here is whenever you have 2 events that happened either together or being asked this and then this, the word and usually means multiplying probability. Last night you saw a phrase that said or probability means you would add your fractions because it's a higher probability of that happening just because it could be either this or this. The word and usually implies that it's going to be a smaller chance. Next, selecting a marble, then choosing a second marble without replacing the first marble. That would be definitely dependent event. Okay, because if I took out a marble, left it out, the total number or the total outcomes have changed. All possibilities have changed. It went from, let's say, 15 marbles to 14 marbles. So because of the new setup, you went from 15 to 14, that is dependent because the second pull of the marble depends on what you pull out of the first one. So that would be a dependent event. Okay, so without replacement, what is the probability of selecting M and then A? So this without replacement, so I'm not replacing it, I'm not putting it back in. That's going to be a dependent event. So let's do the math here. Probability of M and then A, that's going to mean you're going to multiply. Okay, you're going to multiply. So the probability of M right now, so let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in the word mathematics. And I see 1 M, 2 M's. So it's 2 11ths. Okay, and then I'm going to keep that in there. So then an A will be 2, 1, 2, 2, 10. Okay, pick right here, this 11 to 10. This is all theoretical. I went from 2 out of 11. I pull it. If it's an A or if it's an M, perfect. If not, leave it out. Regardless of it, if it's an M or not, I leave it out. And my denominator changes from 11 to 10 because I decrease, I didn't put it back in. Okay, so without replacement means I don't put it back in. So then from here, I'm going to multiply. 4. 2 times 2 is 4. And then 11 times 10 is going to be 110. And I have a 4 out of 11. 4 and 110 theoretical probability of getting an M and then an A. And right here, you should be able to say, oh, I think that's where I can reduce that, right? Because 4, 10, I should be able to reduce both of that. I'll go ahead and divide both by 2, and I get 2. And then you can grab a calculator here, and you can do 110 divided by 2, and you get 55. So I have a 2 out of 55, 2 in 55 probability of getting an M and then an A. If we're going to convert that into a decimal and then to a percent, just go 2, numerator divided by the denominator, 2 divided by 55. You get that. Okay, and then you get 0, approximately 0.036364. If I multiply that by 100, I would approximately get 3.63%. So 3% of the time, you should get an M and then an A. Again, not very high probability because this has to happen first. In this case, the M has to happen first, and then the A. So imagine if we're sitting there, we're actually trying this, all right? Anytime you don't get an M, you're going to keep it out, and then you're going to keep doing it and keep doing it, and next thing you know, you're going to start running out of letters to play with. So without replacement, that's going to decrease your denominator from the start to the next one, and then if you do it a third time, again, you just keep decreasing your denominator. Okay, last one. A red card is drawn from a standard deck, 52 playing cards. If the red card is not replaced, okay, not replaced, that is going to be dependent. I'm not going to put it back in. So I would go from 52 cards to 51 cards. What is the probability of black and then red? So I know that there are 52 cards. Half of them is going to be black, and then the other half is going to be red. So I'm going to multiply that. And then we just figure out that 26 out of 52 is going to be black. That's the probability of getting black because half the deck is black. And then after that, to get red, it's going to be 26 over 51 because I'm not putting it back in. So I went from 52 cards to 51 cards. And then from here, we just multiply our two fractions. And we get 26 times 26. We get 2,704. And then I get 52 times 51. And that is going to be 2652. Doesn't seem right. Sorry about that. I was like, wait a second, that didn't seem right. It totally doesn't make sense, right? Because for some reason my numerator was like way bigger than my denominator. So 6, 7, 6. And then we can reduce this down. Keep dividing by 2. Keep dividing by 2. I'll go ahead and do it on my calculator right here. 676 divided by 2652. And it's going to be reduced down to 13 out of 51 theoretical probability of getting black and then red is 13 out of 51. Okay, and then we can change that into a decimal. That's going to be approximately 0.2549. Multiply that by 100, or move your decimal twice to the left. Excuse me, move it twice to the right. So that would be about approximately 25 and 49 hundredths of a percent. So 25% of the time, about 25% of the time, when you pull out a card, it's black, leave it out, pull out another card, it's going to be red. 25% of the time. Okay, so to review what we just kind of went over today, experimental probability. It's a probability of an event, number of times something happens versus total number of trials. This is kind of like our law of averages, right? Because if we're going to be trying to figure out and predict how well, let's say, LeBron James is going to make his free throws, again, all seasons we collected how many times he shot it, and then we figure how many times it actually happens, and then we kind of go from there and we can predict how well, if he's going to make the next one or not. Then today we also went over compound events, which is 2 or more events. And the math, guys, the math right there is going to be, you're just going to be multiplying your fractions. Okay, so general rule of thumb is if you see the word and, probability of A and then B, or probability of A and B, you're going to multiply your fractions. What I mean by that is if you saw something like what is the probability of, let's say, probability of, whoops, sorry about that. If I need to figure out the probability of, heads and heads, or you can do like probability of heads, heads, heads. Okay, that's going to be 1/2 times 1/2 times 1/2, which would then be 1/8. So your independent events of 1/8 times, you will get heads, heads, heads. Now think about this. If you actually experiment with this, okay, you flip it, not heads, you have to reset. You flip it, not heads, you have to reset. The moment you get head, you can flip the second time and hope it's head. You flip it, not head. So every time you have to reset. So that's not just 1 out of 8 like flips. That's out of 1 out of 8 sets, or in this case, events. Okay, so dependent events. That's going to be something like when you see the phrase without replacement. And then for independent events, you'll see the phrase with replacement. So I know that I kind of went through this pretty quick, and you guys are probably bored out of your mind. So I already went ahead and uploaded this to your Google Classroom so you guys can watch it right now. Again, take better notes, write down more examples, and then begin the assignment. So good luck and ask for hope, and I'll see you guys tomorrow. Thanks, guys.